where we ended yesterday was looking at our reduction. So we would look at an overall reaction and say what things have changed. We've added hydrogen across the double bond. Okay, so we got a hydrogen up here and we have a hydrogen down here. It's kind of an odd reagent or an odd sequence, because if we think about this, the hydrogen up top is most likely what charge? Probably came in as a positive. Why is a positive? Because the oxygen started as a partial negative. How about the hydrogen at the bottom? Probably came in as a negative. Why did it come in as a negative? Because the carbon on the carbonyl was positive. Okay, so initially we may be fine, okay, that makes sense, but then we should step back and think, okay, H+, is that something that we can find? Yeah, H+ is fairly standard. We can find that off of acids. It's relatively quickly and readily available. H-, not so readily available. That is incredibly reactive, because we have a point charge. We've put a lot of electron density in a very, very tiny space on an atom that can barely hold on to its one electron that it started with, hence it typically goes to H+. So to get in an H- as a nucleophile, that's a little bit tricky. Right? And we have seen where it could potentially react before, but to do that, that was in bullet 3, we had to add a catalyst. We had to add a metal catalyst to kind of bring everything in and say, okay, now you play nice and actually do the reaction. Right? Without that metal catalyst, it's not as easy to drop that hydrogen in on, say, our alkenes or alkynes. So this is where these next two reagents come in, sodium borohydride and lithium aluminum hydride. Okay? Lithium aluminum hydride is always a two-step reaction, and Sapling, for some reason, I haven't had time to figure it out, is showing it as a three-step. So you do your lithium aluminum hydride, LAH, followed by ethyl acetate. This is the one I can't figure out yet, why it's there, and then followed by water. Okay. Sapling's doing that. Like I said, I don't know why. Typically, you'll see it as just two steps. Lithium aluminum hydride followed by water, and we'll talk about why it's required 2 steps minimally. Okay. Both of those reagents will supply H-, and that's what we talked about yesterday. If we look at borohydride or even lithium aluminum hydride, they both have the same general skeletal structure. We're looking at boron or aluminum being sp3 hybridized, and both of them don't want a full octet. They're happy at 6 electrons. So that's what's shown in that next, or that image right next door. Okay, what we have here is just BH3, okay, which is the same as, equivalent to, aluminum, or AlH3. That empty p orbital we can put electrons into, and that's what ends up happening in the case of our hydride reagents. We take our hydride, which is highly reactive with those 2 electrons, and we stabilize it by bringing in that empty p orbital. Okay, so we can dump those electrons in there and stabilize them long enough that we now have an active reagent. This reagent is very, very polarized, as you might guess. Our hydrogen comes in as a very strong partial negative, and our aluminum or our boron come in acting like a partial positive. Okay, they aren't formally positive, but they're acting like it because they have that empty p orbital. This strong polarization means that when they react with something else, that something else also has to be strongly polarized. So when we look at the reactivity of our sodium borohydride and our lithium aluminum hydride, they need to react with a pi bond that's very, very polar. Well, what kind of pi bond generates a very polar pi bond? Okay, that's where we can look at our aldehydes and ketones. Whoops. Both are aldehydes, okay, which you should be starting to remember all of your functional groups. Your aldehyde and your ketone, we're looking at carbons out to the side, are very, very polar. Why? The oxygen is very electronegative, drawing that electron density away. Okay? That makes the oxygen very negative and our carbon very positive. If we correlate this back to the reagent that we're now adding in, the positive carbon matches up with the the negative hydride. We don't want to say hydrogen because that tends to imply a positive. Hydride is where we're looking at the negative. Right? The negative oxygen pairs up with the positive boron or aluminum. Okay? Typically, these reagents, when we look at the mechanism for both the borohydride and the aluminum hydride, is you almost always see people write it out as we just take H minus. The H minus comes in and directly attacks. Oh, now we've got our alcohol. Okay? And then this goes up, and then we can pick up a hydrogen from somewhere in solution, and we've got our alcohol. It's a little bit better if we go through and draw that out, because really we aren't looking at H minus existing in any strong amount. So what I'm going to go through and do is take our aldehyde, and I'm going to rotate it on its side. So the hydrogen is now coming at us. The carbon is now going away. There's our oxygen. So we have our p orbitals now in the plane of the board, or the plane of our paper as we write. And what will end up happening is our reagent, either the lithium aluminum hydride or the borohydride, will align such that the electrons from our hydride, can attack to our carbon. The electrons from our pi bond can come out and attach to the boron, and what we end up with, our boron reagent, there's our new hydrogen and carbon. Okay, that boron-oxygen bond is very, very weak, so the oxygen can take the electrons away and react with a hydrogen that it can pick up from solution, which when we look at the longer mechanism for our lithium aluminum hydride, we'll discuss that. Okay? That kind of pair-up allows us to see the dynamics of that reaction. You'll notice that this reaction runs very similarly mechanistically to the hydrogen and platinum catalyst reaction. When we reacted our hydrogen with platinum or palladium, where did the hydrogens add across the double bond? The same side or opposite sides. They added to the same side of the double bond. What's happening in this case? Our hydrogen and our boron, or our aluminum, are getting added to the same side again of the pi bond. And it has to do with the reactivity of each of those pieces. Okay, our hydride is just highly unstable. So to get it to react, it has to be pretty much carried into the reaction site to allow for it to occur, to allow for that transfer, which is why we tend to get that syn addition, okay, or same side addition. All right, questions with the boron? As far as reactivity goes, our sodium borohydride will only react with ketones and aldehydes. All right, remember, the carbonyl class is just the carbon-oxygen double bond. A lot of functional groups have carbon-oxygen double bonds. Okay? Borohydride will only react with the ketones and aldehyde functional groups. Okay? When we move up to lithium aluminum hydride, mechanistically we get pretty much the exact same thing. However, lithium aluminum hydride is really, really reactive. Okay? Anybody speak German?
I can count in German.
Uber is German, right? I think Uber is for super. Okay, so it's super reactive. Just a kind of a translation issue there. So it will react with every carbonyl. So if there's a carbonyl in the compound, lithium aluminum hydride will react with it and will reduce that carbonyl. Okay, every single time. So we got to watch out for that within our reactions. Okay, so if we've got a carbonyl that we want, or if we have multiple carbonyls in our structure and we only want one of them to be reduced, we're going to have to decide what reagent to use, be it lithium aluminum hydride or the sodium borohydride. All right, so let's crank out a mechanism with this functional group. What's the functional group shown now? It's the ester functional group. It's a carbonyl where one of the atoms attached is an oxygen, and that oxygen is attached to a carbon. Okay, so we're looking at the ester functional group. Your lithium aluminum hydride will also react with carboxylic acids. That R group becomes a hydrogen, and we now have a carboxylic acid. Right? So that also brings in another issue with it. So mechanistically, we're doing the exact same thing as we did before. So what I'm going to do is, again, kind of simplify. Our lithium aluminum hydride really just brings in H-. So we'll just start with the H- and say that goes through and attacks the most positive carbon, being our carbonyl carbon. How many bonds does that carbon now have? It would have 5 bonds. That's one too many. So we have to break a bond. What bond do we break? Why do we break the double bond? It's the highest energy bond. So what we're actually starting to look at here is the reactivity of carbonyls, which is officially the next sequence of material. Okay? Our carbon-oxygen double bond, that pi bond is the highest energy. That is going to be the first bond we would break. Those electrons will move to our oxygen. We can now draw the result of that. What else needs to show up? Charge. We have a formal negative charge on our oxygen. Okay. This structure is related to, again, another functional group that we'll talk about in the next section. It's related to the acetal functional groups. Acetals are unstable, and it really kind of centers around that carbon. That carbon now is sp3 hybridized, and it has 2 very electronegative elements attached to it, both of those pulling the electrons away. The sp3 hybridized structure has such a low electronegativity that that carbon now starts to panic. The atom itself says, I need more electrons from somewhere. Okay? It can't accept electrons from outside. It's got to find electrons from within the structure. Where within that structure is the best source of electrons? Oxygen. Which oxygen? The one with the negative charge. So carbon fights and claws and grabs those electrons back. But now what happens? Now it again goes back to this 5 bond issue. Okay, so what does it do? Nope, it's not resonance. If it was resonance, then we could draw this structure and we'd be happy with it, but it has 5 bonds. 5 bonds is a bad structure. As with all 5 bonded structures, what's the next step? You have to break a bond. What bond do you break? Okay, let's go through and look at our options. Okay, by saying the hydrogen, what you're telling me is that we're going to take the electrons that are in that bond to the hydrogen and we're going to put them on the hydrogen.
What do we do with the oxygen?
The hydrogen isn't going to be willing to take those electrons. Yes, we'll get back to you, but you're right. The hydrogen's not going to be particularly happy to do that. It could do it, but that does take us all the way back to the beginning and right back to where we started. We had an uber-reactive lithium aluminum hydride structure. We had a negatively charged hydrogen. It didn't want to be negatively charged, so it reacted. Okay, so while that is a possibility, that doesn't take us anywhere. All right, so that was a mistake.
So the oxygen takes the hydrogen.
Okay, what oxygen?
The negative charge oxygen.
That doesn't fix the carbon's issue. The carbon's issue was that it needed electrons. So it had to take electrons from that negatively charged oxygen. That is happening, period. You don't have a choice. So now the question is that carbon has too many electrons. Something has to take the electrons away from it. We tried the hydrogen. That took us backwards. There's 2 options left. What are those 2 options? The oxygen or the carbon, so left or right of the structure. Okay. Which one takes the electrons?
The oxygen.
Why the oxygen and not the carbon?
This is more electron.
pulls the electrons tighter, meaning it has a higher electronegativity than carbon. We would expect those electrons to go towards the oxygen. All right. What we're trying to do is develop what happens in this reaction. So let's draw it out and see what the result is. Are we done? We need the negative charge. How good of a leaving group is this guy? What was that? It's an awful leaving group. Oh my gosh, it's an awful leaving group. It would never happen. Wait. Look at your starting materials. Okay, what did you start with? What was the most reactive thing that you started with? Hydride, H minus. What's the most reactive thing that you end with? O minus. What happened to the relative reactivity? It went down. We started with something that was ridiculously reactive, and we ended with something that, in comparison to it, was much less reactive. What does that mean about the effectiveness of this reaction? Is this a good thing to do? Yeah. Okay. Yes, we have a horrible leaving group, but in comparison to the solution that it's in, it's a fantastic leaving group. So when we talk about leaving group abilities at the beginning of, or at the end of last semester and towards the beginning of this semester, we were really looking at kind of leaving groups in general. We never looked at what they were compared to. Okay? Now we start having to worry about what are we comparing that leaving group to. Okay? And we've seen this already. Nitric acid acts as what? What does nitric acid act as in general? Focus on that first. An acid. Hence it's called acid. What happens when I put nitric acid in the presence of sulfuric acid? Now nitric acid acts as a base. So even though nitric acid is a strong acid, we can force it to act as a base. Same thing's happening here. This oxide ion is a horrible leaving group. But if I put it in the presence of even worse leaving groups, it doesn't look so bad. Okay? So we have to kind of look at our reactions, both or across the reaction now, not just in general. I know, a lot more challenging. What was the end result of our reduction reagents, both the sodium borohydride and our lithium aluminum hydride? When we talked about it to begin with, the whole goal was to make alcohols. Do we have an alcohol? No. What do we have? We have the aldehyde. We don't really care about this group at the point, or our leaving group at this point. Okay? It will become relevant later, but what we've got there is just a negatively charged species. What's the issue with the aldehyde? It's not an alcohol. Okay? It's a carbonyl. What do carbonyls do in the presence of lithium aluminum hydride? They react. They get reduced. Okay? So let's say we ran this reaction. 2 esters, 2 lithium aluminum hydrides. After one reaction cycle, I have 1 lithium aluminum hydride left, 1 ester, 1 aldehyde. What does the lithium aluminum hydride react with? The aldehyde or the ester?
I'd say the ester. I'd go with ester. It's more reactive than carbon.
Okay, I like what you're thinking. You're looking at the carbon from our carbonyl, right? Okay, and you're saying the ester is more reactive. Why? Why is it more positive? 2 oxygens pulling electron density away inductively. Before we look at the inductive effect, what do we have to look at? Resonance. Does our ester have resonance? Yes. The oxygen, Okay, our singly bonded oxygen can donate electron density in towards the carbon, doing what to the effective positive charge on the carbon? Neutralizing it, which means it's not as reactive. What does our lithium aluminum hydride react with? The aldehyde preferentially. So what ends up happening is we now go through a second reduction, doing pretty much the exact same thing, except now we don't have a leaving group. Okay, well, actually, here, let's just draw it out. So we'll switch to blue now for our hydride. Comes in, attacks, kicks out the electrons onto our oxygen. What do we have left? The charge. Right. We can do the same evaluation that we did earlier. Do we have the acetal? And I know we didn't define what acetal was. I just said what we had up there was an acetal.
Yeah.
For it to be an acetal, I have to have a carbon that's attached to two oxygens. Two oxygens. Do I have that now? No. So I don't have the acetal, which means I don't have the instability that I had with the acetal. Okay? Even if the carbon said, hey, I want some electrons, and tried to take the electrons back from the oxygen, what happens? We end up with that 5-bonded situation. Do we have a good leaving group? Do we even have a remotely not horrible leaving group? No. We got nothing. The reaction stalls. This species can't react any further. We're now done as far as lithium aluminum hydride goes. Are we at the alcohol yet? No. Huh. How do we get to the alcohol? Lithium aluminum hydride was a 2-step reaction. We follow it up with the second reagent being water. Water in this case will act as an acid to donate a hydrogen to our oxide, and we end up with our final alcohol. So esters are tricky. They will react twice in the presence of lithium aluminum hydride. Okay? How many times can a single lithium aluminum hydride react? Why 4 times? There are 4 hydrogens attached to it. In the course of the reaction, those bonds are replaced by our leaving group. Okay? So a single molecule of lithium aluminum hydride can fully reduce a single molecule of ester. Okay? It's not 1-to-1. So if we try and completely react lithium aluminum hydride, 1 mole of lithium aluminum hydride will fully reduce how many esters? 2 esters, because we need 2 reductions in each of those steps to get it all the way down to the alcohol. Okay? And the lithium can do it 4 times. Okay? Let's say we started with a ketone. What would our ratio be then? 1 mole of lithium aluminum hydride can reduce how many ketones? Let me draw a quick ketone up here. We're reducing it, so we're turning it into the alcohol. I know that's kind of crowded. Can't really see it. Very top of the screen. How many lithium, or how many ketones can be reduced by lithium aluminum hydride, by a single lithium aluminum hydride? How many ketones can be reduced? 4. All 4, because lithium aluminum hydride brings in 4 hydrides. Each of those reductions only takes 1 of the hydrides. So we could reduce 4 ketones. Okay, so when we look at the reagents, sometimes we say, well, we only use half the amount or half this. Our lithium aluminum hydride is so reactive that we can't really predict it very well as far as balancing it out. If we throw lithium aluminum hydride in an ester, what do we end up with? An alcohol. Right? We cannot stop it at the aldehyde. Okay, we will go all the way to the alcohol. Okay? Questions with the lithium aluminum hydride, or LAH? Okay. Why is lithium aluminum hydride so much more reactive than sodium borohydride? Okay. And in a lot of why circumstances, what we need to do is identify the differences between them. So I'll give you a moment to kind of think about this. Ideas? Give me some ideas. It's lower on the periodic table, which means what? It's easier to react because it's bigger, which means if we look at our hydrogen being bound on the outside of that, that hydrogen, or our hydride, is now where in comparison between these? It's easier to pull off because it's further away. That bond has become drastically weaker. Okay, so that's a really big difference between our, I don't know why I didn't draw. I was probably working on it. Between our aluminum and our boron. Better not completely freeze up on me. I'm really upset. Okay, what else is a big difference between these?